Let's look at the work done by force due to gravity, or the weight. So again, let's go back to the definition. W is R1, R2, sum of the forces dr, and we will consider the force due to gravity. And when we're dealing with work and energy, we will always use y going up. Therefore, when you pick a current system, and it's very different from doing Newton's forces, where you are always free to pick any current system you want. You could pick y positive going down or going left or at an angle of 45, doesn't matter. When you start doing energy analysis or work analysis, the result that we're going to derive always assume that you're picking positive y going up. So please remember that. Whenever you do work or energy, always pick a current system which is going positive up. So this is what you need to pick. Okay, so that we can use the result that we will derive. So in this case, we're dealing with a force due to gravity, so this resumes to minus mgj, because you know that the force due to gravity is in this direction. Now dr is, in this particular case, dy or dyj, because as the weight is applied to a particular object, since the force is directed down, it's either going to go up and down. If another force is being applied to counteract the weight, it's going to go up. If the weight is only one, it's going to go down. So dr is just dyj. So let's plug those two into our work equation. Since dr is dy dj, then really I need to move my r1, r2 with y1, y2. My force is minus mgj, and my dr is dyj. Scatter, scatter, vector, vector, j dot j is 1, therefore my work is on nothing else than y integral from y1 to y2 of minus mg dy. Okay, minus mg is a constant, so we can take it out. y1, y2, dy. This is trivial. This is just y2 minus y1. Therefore, the work is equal to minus mg y2 minus y1. Now, let's look at this carefully. Let's imagine that I decide my coordinate system to be centered at my y1 position. And again, I need to choose it up. So let's say y1 is equal to 0. Then really the work done in this particular case is just minus mg y, and y refers to wherever position I brought my system to. Let's take the case where I'm bringing my step up. So I'm going against gravity. My dr is going up, and my force due to gravity is in the opposite direction. You know right away that as you calculate the work the work due to gravity, since gravity is opposite in direction as dr, you expect a minus sign. Up, here it is. Y is going to be something positive value, let's say 1 meters, therefore this is positive, the work is negative. So as you bring a system up or against gravity, then the work done by the force of gravity, Fg or W, is expected to be negative. If you bring an object in the other direction, that is, you let it drop, so its position will go from this position to this position, then in this case the work is going to be minus mg y2 minus y1. Your initial is, say, here 1 meter, your final is, say, here 0, the final is 0, the initial is 1, therefore this is negative, right, because your final position is less than your initial if you're going down with gravity. So if this term is negative, you multiply this term by the other negative, and the work end up being positive. So, two main scenarios when you deal with work and gravity. If you're bringing an object up or against gravity, the dr is up, gravity is down, therefore you expect the work to be negative. If now you bring an object down with gravity, your dr is down, your weight is also down, same direction, you expect the dart product to be positive and therefore the work to be positive. Please do not memorize those two cases, just think about it. Imagine a little free body diagram in your head. Imagine, okay, I'm going up, my dr is up, my w is opposite, I know my work done must be negative. If an object is falling down from one position to the other, you know your dr is down, you know that the weight is also down, therefore w is positive. So think of it that way. Imagine a little coordinate system, a free body diagram in your head, and deduce the sign or predict the sign that you're gonna get just by picturing your free body diagram. Do not waste your time memorizing this. Similar rules will come back in kinetic, or I'm sorry, when we do potential energy, which is another type of energy, and it will be exactly the opposite. So if you try to memorize it, you're gonna have two opposite rules depending on whether you deal or think of it as work or energy. So it will be confusing. So unless you have a perfect memory, and it's no problem, don't memorize it, just make sense out of it. It would be much easier not to make mistakes. Am I done here? Work, oh yeah. Oh no, one last thing. Look. Work is minus mg y2 minus y1. All we care is initial position, final position. Whether we went or we went, same work done. So the work done by weight is independent of the path. We call this conservative force, which is exactly the same as the force due to the spring, which was minus k over 2 times final position squared minus initial position squared. Those two forces are called conservative forces because as you calculate the work, you don't need to know the path. You just need the initial and the final position. So usually for conservative forces, the work can be obtained without knowing the path. We will see other forces which are non-conservative, and the main example is friction, where of course the path will matter.